So yeah, last time we left off talking about limiting reactants. So just got another problem, or a few more problems that we're going to do here. The previous ones we did, it was just we were given moles and asked to find the limiting reactant based on those quantities of moles. More often, of course, you'll have grams. So if we have this reaction of sodium reacting with chlorine to make sodium chloride, the way you do any limiting reactant problem is the same. You have to do the stoichiometry for each of them, and then compare the products. And you actually don't need to go all the way to grams. You can go to moles, and that's as far as you really need to go. So if we start with writing both of these out, 53.2 grams of sodium and 65.8 grams of chlorine. Whoops. And we'll draw a line here for stoichiometry. All right, so starting with sodium, what's our first step? Convert it to moles, yeah. Because we have grams, and we want to calculate the quantity of sodium chloride. All right, we're trying to predict how much product we can make. So sodium is 22.99. So that's 22.99 grams of sodium for 1 mole of sodium. So that'll give us moles of sodium. And now we can pull our molar ratio from the chemical equation. So what's the molar ratio of sodium to sodium chloride? 2 to 2. So just make sure that you put these into your equation in the right order, right? Have the right one on top, right one on the bottom. So 2 moles of sodium on the bottom, 2 moles of sodium chloride on top. So that will give us moles of sodium chloride. We do 53.2. Oops. We can skip the times 2, that 2 to 2 ratio, because it is 2 divided by 2, so that'll be 1. So it's going to be 53.2 divided by 22.99. And we'll get 2.31 moles of sodium chloride. And then we can kind of rinse and repeat the same process. We just need to find the molar mass of chlorine. And actually, should point out that this one is a little trickier because it's the mass of the element, the molecular element, right? So it's 2 chlorine atoms. So that means that we have 2 times the mass of chlorine, which is 35.45. So 2 times 35.45. So this will be 70.90 grams of chlorine, Cl2, for 1 mole, Cl2. And then our molar ratio between chlorine and sodium chloride is going to be 1 to 2. So we'll add 1 mole Cl2 will give us 2 moles NaCl. So we do 65.8 times 2 divided by 70.9. So it'll be 1.86 moles of sodium chloride. So what is our limiting reactant? Chlorine. Yep. Chlorine is our limiting reactant because it produces the smallest amount of sodium chloride. which makes this our theoretical yield. Any questions? Is everything coming back from Tuesday? Good. So here we've got the question worded a little bit differently. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? I feel like this is the kind of question that would cause a lot of mistakes. Because remember, the maximum amount that we can make is still the one determined by the limiting reagent. Even though the other one will be a higher quantity, we would run out of the other reagent first before we made that amount. So whenever it's asking for the maximum instead of the limiting reagent, it's still a limiting reagent problem. So do 25.2 grams of nitrogen and 8.42 grams hydrogen. Another thing to note on this problem is that it is asking for the maximum amount of ammonia in grams. So we can start this problem out by going just to moles, figure out the limiting reagent, and then finish the problem. Because if we go to moles, that'll tell us the limiting reagent, and then it's just a matter of converting that into grams. So you can save yourself a little bit of work by not converting both of them. All right, so what is the molar mass of nitrogen? 14 for a single nitrogen atom times 2. So it'll be 28, close enough to 28.00 grams of N2, then 1 mole of N2. And then our ratio of nitrogen to ammonia, 1 to 2. 1 mole of nitrogen, 2 moles NH3. Okay, so that'll get us all the way to moles of ammonia. So 25.2 times 2 divided by 28. We'll get 1.8 moles of NH3. Then for hydrogen, same process. Again, we have hydrogen H2, so our mass here will be 2.02 grams of H2 for 1 mole H2. And then our ratio from our balanced chemical equation is 3 to 2. So 3 moles hydrogen, 2 moles ammonia. So 8.42 times 2 divided by 2.02 divided by 3. We'll get 2.7. I guess this one should have been 1.80. 2.78 moles NH3. So again, what is the maximum amount of ammonia that we can make? 1.8 moles, yes. So we don't need this one. Move this over just a little bit. So now we can just convert moles to grams. Again, we'll need some quantities from the periodic table, 1 nitrogen and 3 hydrogens. So I'll give this 14.00 plus 3.03, 17.03. And that's grams per mole of NH3. So if we want to get grams, we're going to have to divide by moles. So 1 mole of NH3 and multiply by the 17.03 grams. So we get 1.8 times 17.03. That'll be 13.7. Sorry, not 30. Not 13, 30. 13 going on 30. Moles of grams of NH3. Ran out of space. They say the devil is in the details, and that's definitely the case with problems written like this. Just make sure you stay on top of the units that are asked for in the solution. And I try to avoid phrasing like this because it is confusing. Yeah. At least phrasing like, what is the maximum amount of ammonia? And I will always try to add what units specifically I'm looking for the answer in. So I'll just say, what mass of ammonia, and not give you units. Yeah. Good still? Haven't really added anything else yet. Okay. So this reaction used to obtain iron from iron ore. You have we're given 2 quantities, or 3 quantities here. So we have a reaction of 185 grams of iron oxide with 95.3 grams carbon monoxide produces 87.4 grams of iron. Find the limiting reactant, theoretical yield, and percent yield. The trick to this problem is that this is the actual yield. So you still need to calculate a theoretical yield. And remember, we find the theoretical yield from our limiting reagent. So again, since we're still doing a limiting reagent problem, we're still doing stoichiometry, we start it exactly the same way with the quantities, the masses, and grams that were given. So 185 grams of iron oxide, and keep doing this, I should put this up a little more. 95.3 grams of carbon monoxide. Notice that we're not yet using the 87.4 grams of iron, because again, that's an actual yield. So first step for our 185 grams of iron oxide. We'll again find the molecular mass, 55.85 is iron. So if we have, do this up here, iron, oxygen, 2 of those, 3 of these, 55.85, 16.00. This will be 1 117 or 111.7. And then 3 times 16 is 48. So we'll get the addition of those together will be 159.7 grams per mole of iron oxide. So we use this to convert to moles. Then after we convert it to moles, we can use our molar ratio. And we want to figure out the amount of iron, right? Because we're asked for we're given that it produces this much iron as the actual yield. So it doesn't make sense to calculate the amount of carbon dioxide that's produced. It would still tell us our limiting reagent, but it wouldn't be very useful after that. So ratio between iron oxide and iron, 1 iron oxide to 2 iron. And then I'm going to calculate the number of moles, because if this one is not our limiting reagent, it'll save us some time in the long run. Let's do 185 times 2 divided by 159.7. So we'll get 2.31 moles of iron. Same thing with this, 95.3 grams carbon monoxide now. This is going to be 12.01, 16.00 for 28.01. So 28.01 grams of carbon monoxide is 1 mole of carbon monoxide. And then the ratio between carbon monoxide and iron is 3 to 2. And that'll do that. So 95.3 times 2 divided by 28.01 divided by 3. Ooh, it's close. 2.27 moles of iron. Yeah.
How do I know how you said iron oxide, right? Do comparison between iron oxide and iron. How do I know I'm doing those comparisons? Like, how do I know which ones I'm comparing? Does it say right here?
Yeah, I'm not a big fan of the way this one's worded, because it's just sort of implied that iron is that this 87.4 grams of iron is the actual yield. I would word this differently. I would say that this reaction actually produces this amount. Calculate the theoretical yield based on these other quantities. So the reason that you know that you're going to compare these final ones to the grams of iron. Well, actually, sorry, your question is, why iron oxide, why carbon monoxide? No.
It's like, okay, let's say we are like on the second one, and you're like, okay, what's your ratio between the iron and iron oxide? How do I know I'm doing iron oxide? Like, is it saying it right there? I'm just not.
Wait. Oh, you mean carbon monoxide to iron?
Yeah, I'm just saying, how do I know which ones I'm doing? Like, I do sometimes and then I don't, but
Okay.
how do I know that this iron oxide at the top is
Yeah.
going to be compared to this iron here? How do I know that it's not this iron oxide here to just 3CO2 at the end? Do you know what I mean? How do I know that?
Yeah, so why is it this iron and not CO2?
Yeah, or how do I know which ones I'm comparing?
So in this case, we've been given a quantity of iron that is actually produced. So we're going to use each of our reactants that we've been given quantities of to calculate a theoretical yield of iron. Because then so we figured out now that based on these, this one is our limiting reactant. So we can convert this 2.27 moles of iron into grams of iron.
Yeah, I have all that.
So let me do that real quick. 55.85. So our theoretical yield is 126. I guess that's all the sig figs we have. 127 grams of iron. So the reason that we're calculating iron for iron oxide and iron from carbon monoxide is that those are the two quantities of reactants that we were given. And then the question's asking specifically this theoretical or percent yield portion. And we can only calculate a percent yield if we're given the actual yield. So the actual yield is 87.4 grams. So there's not enough space. Try this. Shift that guy over. It didn't help much. So it's going to be actual divided by theoretical times 100. So our actual yield is 87.4 divided by our theoretical yield, which is 127. So 87.4 divided by 127 will give us 0.688, but we multiply by 100 also to give us a percent, and it'll be the percent yield. It'll be 68.9%.
Where's your 127? Oh,
Yeah, ran out of space a bit. Are there any questions? Yeah.
Are the reagents and the reactants the same thing?
Yep. I've been writing limiting reactant, huh? Yeah. Limiting reactant. They're the same thing. Yeah.
On the test, well, it's like what you were saying. I was asking for iron on like both of them.
Right.
On the top, will it be more specific on the test?
Yeah. I'll say that this reaction is used to obtain iron from iron ore. If the actual yield is 87.4 grams of iron, what is the theoretical yield if the amounts of iron oxide and carbon monoxide were this and this? That kind of thing. Yeah. Not a huge fan of this wording, but it makes a good point. Anybody else? Yeah.
So, based on the question that we're given, like, it was the first question that we started off with when class started. We'll know how far to go in based on what it's asking. So, how we went from grams back to grams again.
Yeah.
Since it was only asking for the theoretical yield for the first question that we did, that's why we only stopped at moles.
Right. Yeah, so you only need to go 2 moles to figure out theoretical yield. Well, to figure out limiting reactant. And then theoretical yield is dependent on what units of theoretical yield I ask you for. So like on this problem, it doesn't have units for theoretical. Oh, no, it does, sorry. It says theoretical yield in moles. So we stopped at moles. That was the theoretical yield. This question could say in grams, and then you would take this one step farther and convert it back to grams.
Or if it starts in grams, then it ends in grams too, right? So like if the question was different, if it wasn't in moles, like if I'm...
Yeah, well, always go off of, I will always specify the unit that I want you to give the answer in. So it could start in grams, and I would ask you for the yield in moles, maybe. That's a possibility. But I will always try to put it in there. If I don't put it in there and you're taking the exam, please ask me, because that is, I intend to put it in there. Yeah, like this problem we stopped at. So started with grams and stopped at moles. But there wasn't a unit specified. So you could just stop at moles.
So if the unit's not specified, then you just start from what's given and end at moles?
You could. If ending at moles satisfies the question of the theoretical yield, which it would, then yeah, if it's not specified. Are there any other questions? Because we're moving on to enthalpy next. Nope. Okay, so enthalpy, as I mentioned way up at the top, is just a fancy word for heat. Of course, the actual definition is more nuanced than just heat, but for the purposes of this class, you can really think of it as just thermal energy, heat. And we talked a little bit about exothermic and endothermic processes, like way back in chapter like 3 or 4 maybe. Here we're going to kind of put that into practice a little bit more. So an exothermic reaction is one that emits thermal energy, emits heat. An endothermic reaction is one that absorbs thermal energy or absorbs heat. So classic example of the exothermic reaction would be like a fire, right? Campfire is emitting lots of heat. Your car engine gets hot because you're burning the gasoline, which is an exothermic reaction. There aren't very many examples of endothermic reactions. So the amount of thermal energy emitted, or absorbed by a chemical reaction can be quantified. So you can actually calculate exactly how much heat a certain amount of gasoline will produce when you burn it. And it's called the enthalpy of reaction. It's the thermal energy that flows when a reaction occurs at constant pressure. So we haven't gotten into pressure or anything yet, but so it's the amount of energy that flows, and specifically right, that flows. So it could be exothermic or endothermic. It could be positive or negative exchange of heat. And it's the sign of delta H that tells you in which direction the heat is flowing. This again goes back to thinking of the system as our chemical reaction. So if the system is this box, the sign of delta H is telling you which way in or out of that box the heat is flowing. So if energy is flowing out of your chemical system, that's a negative delta H, or exothermic. You can also kind of think of it like your bank account, right? If you withdraw money from the account, that would be like an exo, trying to think of another word for money, like an exo money process. Right? You're extracting money from that system. If you deposit money, so have another system here. If the heat is going into the system, that's a positive delta H, and that's endothermic. So you're adding heat into that system. So as I mentioned already, our exothermic reactions release heat into the surroundings. And if you sort of diagram it out, if this is energy, where higher energy is at the top, if our reactants are starting at this level of energy, after the reaction, they release that energy into the surroundings. So our energy decreases for the system. We end up at a lower level of energy. So like mass, this is another one of the thermodynamic laws, but energy can't be created or destroyed. It always has to go somewhere. Actually, I think we did talk about that, chapter 4. So for the reverse process, in an endothermic reaction, your reactants have a lower energy level, and they absorb energy from the surroundings to have a higher energy level. So they're always taking energy from somewhere or depositing that energy somewhere. So delta H is negative for exothermic reactions. And we can actually add delta H sort of into the reaction and think of it as one of the products, or reactants or products, depending on if it's exothermic or endothermic. So for this combustion reaction, burning reaction, we have methane reacting with oxygen to produce carbon dioxide, water, and heat. So we know this is an exothermic reaction because we have a negative quantity for delta H. That froze a little bit. There we go. Negative quantity for delta H, and in units of kilojoules. So the units for heat will always be in joules or kilojoules. And what this is telling us, what delta H actually is that 802.3 kilojoules of heat are emitted when 1 mole of methane reacts with 2 moles of oxygen. So it's like a stoichiometric quantity, or it is a stoichiometric quantity. So we could rewrite this reaction and include heat as one of the products. We'll call it delta H. Now notice here I didn't put the negative sign in there because it's one of the products. So if this is our system, as we go from reactants to products, these are all now separate entities outside of that system. All right, so they're now 3 separate things. So we made the CO2, we made the water, and we also removed heat from those 2 molecules. The way you know which side of the reaction to put the delta H, if you want to write it out like this, is dependent on the sign. So if we have an endothermic reaction, then we need to add heat to the reaction for it to take place, and it's one of our reactants. All right, so if we have a positive sign here, this reaction is endothermic, so it requires heat. And just like with emitting heat, this is also directly tied to the amount of reactants and the amount of products that are produced. So 182.6 kilojoules of heat are absorbed from the surroundings when 1 mole of nitrogen reacts with 1 mole of oxygen. So you could rewrite this as 182.6 kilojoules. I guess I did this before. Delta H plus N2 plus O2 gives you, oops. H2NO. All right? So the reactants are all the things that go in. So we have to put in the heat, the nitrogen, and the oxygen to have this reaction take place. Any questions so far? So we make calculations of this as well. Because these amounts, the amount of heat, the heat emitted or absorbed when a chemical reaction occurs depends on the amounts. If you burn twice as much methane, you'll get twice as much heat. If you burn half as much methane, you'll get half as much heat. Yeah?
So does the negative or the positive determine where the kilojoule are going to be placed? Because I see that with
Yes.
the negative you place it at the end, and when there was a positive you place it at the beginning.
Right. Yeah, because if you think about it, if you have methane, or if you have a butane lighter, right, you're taking just the butane inside and oxygen, and as you burn it, one of your products is heat. Yeah. And then for the endothermic, if it's a positive sign, yep, it's one of the reactants, or you can think of it as one of the reactants. So delta H, we usually specify delta H in combination with the balanced chemical reaction because it is something that I believe is determined empirically. So somebody had to do an experiment to figure out how much heat that produced. The magnitude of delta H is directly tied to the stoichiometric amounts, which is really a way of saying the amounts specified in the recipe in the chemical equation as it is written. And it'll tell you how much is transferred, how much energy is transferred for the molar amounts in the balanced chemical equation. So if we have this reaction, we're now reacting propane with oxygen. And again, we're producing CO2 and water. And then are we going to be producing heat, or is heat one of our reactants?
It's producing heat.
Producing heat. So it's exothermic, which we know because it's a negative sign here. So if we have 1 mole of propane reacts with 5 moles of oxygen, we'll form 3 moles of CO2, 4 moles of water, and 2,044 kilojoules of heat. So it's, again, another conversion factor that we can use, really just like we use the molar ratios. So if we said, okay, that's for 1 mole, what if we had 3.14 moles of propane? I think you're on the right track. But our ratio here, is going to be the 1, just like we do for the molar ratios. So 1 from the propane and negative 2,044 kilojoules from our delta H. So 1 mole C3H8, negative 2,044 kilojoules. So we'll get a negative 6,418. Well, I'm not going to worry about sig figs for now. Kilojoules of heat. Any questions so far? So you could also figure out, if you had this reaction and somebody said, based on this reaction, or this reaction takes place, 50 moles of CO2 are produced. How much heat was also produced? It's just another ratio. We would just use 3 moles of CO2 to negative 2,044. So you can do it for any of the quantities, just like Just like if you're calculating moles to moles of something or grams to grams of something in the chemical equation, all you need is one quantity to calculate all the other quantities.
Actually, yeah, I do have a question. The
Yeah.
2.14, where'd you find that one from?
Oh, I just made up a number.
Okay, so you're saying, right?
Yeah, it was just an example of not a whole number of.
Right.
Yeah. Yeah, I picked it because it's pi. 3.14. All right. So if ammonia reacts with oxygen, according to this equation, calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So it's just another stoichiometry problem. We'll start with 155 grams of ammonia. And we'll calculate the molar mass of ammonia. Because even though we're going from, ammonia to energy, we're still using the chemical equation, which is still in units of moles, aside from heat, which is in kilojoules. Right? So you can have different quantities, or be careful with what I say. Are we going to come across any other? I think it's just moles. Moles, and we can convert to kilojoules. Right, so ammonia is going to be 14.0? Oh, it's 14.01. So we've got nitrogen, hydrogen. So this is going to be 17.04. So 17.04 grams of ammonia is 1 mole ammonia. Now we can use this molar ratio between moles of ammonia and kilojoules of heat produced. So what's that ratio going to be? Yeah, 4 to 906. So it's just the 4 moles of ammonia to the negative 906 kilojoules. So now you can see we'll do 155 times negative 906 divided by 17.04 divided by 4. This will be negative 2,060 kilojoules of heat. It's just another conversion factor. Uses the same rules as molar ratios and other stoichiometry problems that we've done. So you could also have a limiting reagent problem where it asks, what's the maximum amount of heat you could produce given X moles of ammonia, X moles of oxygen. Right? You just calculate to solve for heat, and then whichever one produces the least amount of heat will be your limiting reactant, and therefore the most heat you could produce. Or I could give you this reaction produces this much heat. How much ammonia reacted to produce that heat? Maybe we'll do one of those. Oh, never mind. Here's a problem there. Perfect. So what mass of butane in grams, so butane in grams, is necessary to produce 1.5 times 10 to the 3 kilojoules of heat? And what mass of CO2 is produced? So, like I was just saying, it's still a stoichiometry problem and really follows the same rules. So we start with our 2,658 kilojoules. a straight line. All right, what's our first step here? Why did I, sorry. I wrote the wrong number down. This should be 1.5 times 10 to the 3 kilojoules. So the other way around, yes. Yeah, so we want to know, well, we want to know two things. We want to know the mass of butane that was necessary to produce that heat, and also the mass of CO2 that was produced. Those are two separate problems, right? We're solving for two separate quantities in this reaction or chemical equation. So we'll have to do two different problems here. So let's solve for the first one first. Let's solve for butane. Still, first step is the same. Well, first step is related to that. So we will divide by the 2,658 kilojoules, but we also need to multiply by something. Oh yeah, they're both 4. So we'll multiply by 4 moles of butane, because we're going to solve for butane first. So negative 2,658. And we're going to multiply by 4 moles of butane. Because that's the molar ratio, right? Okay, so now we've got 4, that'll give us 4 moles of butane. And we're asked for the mass of butane in grams. So we'll need the mass of butane, the molar mass of butane. CH, that's 4 and 10. I'm going to write this out. I might as well write out the whole thing. This is 48.04, 58.14. This is grams per mole butane. So we want grams, so we're going to multiply by grams. 58.14 grams, C4H10. Cool, and we can solve that. 1.5 times 10 to the 3 times 4 times 58.14 divided by a negative, oh, I guess the negative doesn't actually matter here. Well, divided by 2,658, because we can't have a negative grams. So it's going to be 131. Oh, I only have 2 sig figs, huh? It's going to be 1.3 times 10 to the 2 grams of butane. All right, so the second problem that we have to do is now pretty much the same, but solving for a different compound in our chemical equation. So that got us butane. Like I was just mentioning, you can use the one number that you're given, you can use one quantity to solve for any of them. So a ratio here is going to be the ratio from heat, joules of heat, to the molar ratio in the chemical equation, which is also 4, but 4 moles of CO2. And then the molar mass of carbon dioxide, 12.01, and we have 2 oxygens, which will be 32.00. That's 44.01 grams per mole CO2. So we'll just multiply by those grams. So 1.5 times 10 to the 3 times 4 times 44.01 divided by 2,658 for 1.0. Oh, no. Yeah, 2 sig figs, okay. 99 grams of carbon dioxide. So you could go on to solve this for water and oxygen also.
What made you determine the amount of sig figs? Was that the first 1.5?
Yeah, it's the first 1.5. So yeah, for these, molar ratios are exact ratios. All right, you need exactly this many. You need exactly this many butanes to react with this many oxygens. Now I wouldn't change the answer. This is weird. But if you multiply the whole thing by 2, you're going to end up with the same answers. So I don't know why. Yeah. Fractions are tricky. Well, that was the last problem. And just a note to help you out in the homework, the absolute value of heat is requested, and then they use words to convey the sign. So tell you that they'll say it's this amount of heat that's produced in an exothermic reaction would be a negative sign. Or if it's this amount of heat, so if it was, just making up another number, 1,440. Yeah, if it's an endothermic reaction. What? There it goes. Endothermic would be a positive 1,440. Exothermic would be a negative 1,440. So, or that heat is produced or heat is absorbed, right? So produced, absorbed. If it's what? Okay. Produced would be negative. Yeah.
You would think produced would be positive.
Yeah, but again, it's from the perspective of the system. So it's the heat is coming out of the system. So it's negative. Yeah. Any other questions on this stuff? No? I made up a number. Yeah. Yeah.
Is the answer always going to be positive?
Yeah, so like for this one, even though it's a negative, like that is the amount of heat produced and it's negative, because it's an exothermic reaction, you can't have a negative quantity of grams. So
So even though the answer is not negative, you just change it to positive?
yeah, I was trying to think of the logic for how would you justify that other than knowing that grams can't be negative in this case. Just know, yeah, if you're going from energy to a quantity of moles or grams, it has to be positive. Yeah. Okay.